Greetings. My name is Howard Chorney. I'm a member of the Shunra Performance Engineering team, and I'd like to welcome you all to Front-End Performance Engineering Basics, the network. Let's talk about the difference a wide area network makes when we're accessing applications across a wire. Let's take this example. We have three sets of users. A set of users are in Tokyo, a set of users are in London, and a set of users are in New York City. The data center is located in New York City. Will each of these users accessing the same application in the different locations experience that application the same way? The answer will be no. And what we're going to do is talk about why our users in Tokyo and London will not experience the application the same as in New York. There are several different network conditions that will actually inhibit the flow of data from point A to point B. What we're going to do now is discuss those. And there are 5 major points that we will be addressing in this module. The first impairment is network delay, which is also known as latency. Our second impairment will be jitter, and we'll be talking about that too. Packet loss is another large contributor to network delay. Then we have our bandwidth constraints and our bandwidth utilization. So let's start talking about latency. Why is there a latency or network delay on the line? Latency is basically the delay between point A and point B. The base factor of latency is the law of physics, okay, which is also known as propagation delay. And as you can see from the slide here, data flows from point A to point B at the speed of light. Now, this is the optimal or minimal effect of latency. This effect is also caused in a vacuum. So if we were to go from New York to London in a vacuum under perfect conditions, we would experience about 28 milliseconds worth of latency delay or propagation delay. And again, that's the physical time it will take a packet to go from point A to point B. Now that's in a perfect world, and again, in a vacuum. But as we know, we do not pass data in a perfect world from point A to point B. There are many factors that happen when we're passing that data from point A to point B, which increases that effect of latency. One common thing we all know about is routers and switches. Packets will flow through a router or a switch, and then what will happen is that router or switch could get busy. Once that router or switch gets busy, packets will queue up behind that router or switch, waiting for that router to process the data to let it flow through. This, in effect, will also add to that latency. So then there's another piece of delay that goes into that optimal or optimum latency delay. Here's an example of signal speeds between point A and point B. And we will be able to see that this is the utopian world, and as we know from our experience, these are really not true numbers. And this is actually without going through any equipment at all and just going in a vacuum itself. We have 5 major cities: New York, London, Frankfurt, Tokyo, and Sydney. You'll see that here we have the distances between New York and the other remote sites. Theoretically, our minimum signal time one way looks like this. So you'll notice, as I said before, London was about 28 milliseconds. And again, that's perfect conditions in a vacuum. Now, we all happen to know New York to London, we've never seen traffic flow at 28 milliseconds. If we look at Sydney, we'll see New York to Sydney is 80 milliseconds. Again, a little bit on the utopian side. I would say that in most of my experience, I've seen latency between New York and Sydney one way at about 160 milliseconds. Again, the reason why is this is in a vacuum, but in the real world, we are sending packets through routers, firewalls, all these other things. So just to review, minimal effect of latency is in a vacuum, but once we start adding network hardware and signal strength and repeaters into the mix, there is a time cost to traverse each one of those pieces of network equipment. Next thing I'd like to do is talk about packet loss. Now, packet loss is very much affected by latency and also contributes to latency. So packet loss basically is the inverse of delivery rate, okay? So in the perfect world, we would deliver 100% of our packets from point A to point B, but due to a lot of different factors, that's not possible. So what happens is internet service providers will actually go out and spec packet loss. And packet loss, at least in the United States, is pretty much guaranteed at a 99% or better delivery success rate versus 1% packet loss. Under 1% in the US, again, is considered acceptable. Other parts of the world, there are different specs for packet loss. Now, let's examine the reason why packets get dropped on a network. First and foremost are, and I think we've already seen this in a couple of slides back, our network congestion causes queues to saturate, right? It's just like traffic on the road. If there's more traffic than the road is able to handle, things start to queue up. Same thing with packets. If there are too many packets on the wire and you only have the capacity to handle so many packets, packets will queue up. Once those packets queue up, obviously it takes longer to get from point A to point B. And what happens there is sometimes packets will drop out, as packets usually will have something called TTL, or time to live. That packet will lose its signal strength, it will pass its time to live, and effectively be lost. Next thing is, anyone using any sort of monitoring devices out there may have their queues set for red, random early detection. What could happen during a random early detection event is a piece of network monitoring hardware or software will recognize that a queue is starting to saturate or a line starting to saturate, and it may switch that line to an alternate route to alleviate that congestion. Unfortunately, during that switch, what happens is you will have packet dropouts during that switch time. The next thing I want to talk about is interference on wireless networks. Now, I don't know about you, but anyone who uses a mobile phone or remote phone definitely understands about interference on wireless networks. Wireless networks are not perfect. They're very subject to atmospheric conditions, traffic conditions, how far you are from a cell tower. This will definitely cause packet drop, and probably at a higher rate than 1%. Next thing we can talk about are hardware errors. Face it, hardware errors happen. Chip's hardware fails. What happens when a packet's going through a piece of hardware that fails? The packet gets lost. Sometimes with routes getting congested, weird things happen to hardware. Again, the packets get lost. So hardware error is a very normal way for things to happen. The last thing I want to talk about for packet loss are firewall policies. There's definitely a cost for a packet to traverse through all the conditions it must meet to go from the outside network into your intranetwork. And people don't understand or even think about that there is definitely a cost delay as these packets are going or checking through their decision statements in a firewall. Thus, the more firewall policies you have on your firewall, the more of a delay you could cause. So to review, we've discussed packet loss when the network is congested, packet loss when we have to fail over to a different route, packet loss when we have interference on a wireless network, packet loss when we have hardware errors, and packet loss due to firewall policies. Next thing we'd like to do is talk about jitter. Now, jitter can manifest itself in a couple of different ways. Basically what jitter is out of order packet delivery. Now, your packets are getting delivered true from point A to point B. However, if the packets get delivered out of order, there is a cost at the target end that will have to reassemble those packets before it can present the data stream to the end user. So naturally that assembly time is going to cause more of a delay. So that is actually called inter-packet gap variation. Now, packet delay variation will happen as a wire is never constant. There's always activity going on a wire, and we'll actually see an example of this shortly. And what happens is latency varies from point A to point B because of all these things. So again, that causes a packet to get delayed and packets to be delivered out of order. Let's show an example of that. So here you'll see a line with no jitter. Packets are flowing in order. They're traversing the wire. Here's that same set of packets with jitter. Notice the speed variations. Notice how the packets are now being delivered out of order. Again, what has to happen is when those packets get to their target destination, they have to be reassembled properly, hence adding more delay. There are a couple of applications that are very, very sensitive to jitter. That is voice and video. Now, could you imagine if we were doing voice over IP and we were having a voice conversation with a lot of jitter going on? It would be pretty funny. Like the conversation could go, "Hello, Graham, are you, how, day 2? Obviously would not be a very effective conversation. And actually think about jitter too. If you're watching streaming video, it would be pretty bad if your video was delivered out of order. It would make the story a little nonsensical, wouldn't you agree? So again, your packets must reassemble themselves in the buffer on your target machine before it'll be displayed to you, causing delay, in some cases causing a very choppy video. Let's look at some examples visually of network delay and what network delay looks like. What I have here is basically a trace. As you'll see, the green line represents latency. The red line represents packet loss. You'll see in this trace that basically data transmission stream is pretty constant. There's not a lot of activity on the line. Therefore, there's not a lot of packet dropouts happening, not a lot of jitter happening, and data will be flowing pretty freely. Now I'd like to show you an example of a line that has a little bit more activity and has some jitter on it. And you'll notice the jitter by the spikes in the green line. You'll see latency isn't constant. There are some activities going on the line that are causing this jitter to occur. But basically you'll notice here that our packet loss is not that high. Thus we're still getting a pretty clean transmission. Now let's look at a different type of line. This is a line with a lot of activity on it. You'll see that packet loss is high, jitter's high, and you'll also notice that jitter and packet loss are ever increasing as the transmission goes on. This is what I like to call the death spiral of latency. What happens is, as latency increases, your packet loss is going to increase. As you'll notice here, as latency increases, packet loss increases. And it just basically spirals from there. So let's talk about the reason that this happens, and especially why it happens in TCP. So ask yourselves, with TCP, what's the advantage of using TCP/IP? That's right. Of course, the advantage is that we get confirmation that our packets have been delivered. So if a packet drops out, we're not going to get confirmation that that packet was ever delivered. What's going to happen is our source is never going to get confirmation, so it's going to rebroadcast those packets. As it's rebroadcasting those packets, it's putting more traffic on the line because now we have the normal data transmission going on, we have retransmits going on, thus the activity on the line increases. As the activity on the line increases, the delay is going to increase because more packets are on the line and we could get into saturation conditions. Hence we get into, again, what I call that death spiral of latency. It will definitely not go on infinitely. There will be a point of massive failure and we'll have to start the process all over again. My final example is a pretty interesting example. So let's look to see what's happening. Traffic's going along pretty normally without much delay. And then all of a sudden there's some sort of event where latency skyrockets and our packet loss starts to go up. Does anyone have an idea what may have happened in this situation? What's happened is we've actually had a catastrophic hardware failure. During this catastrophic hardware failure, this caused our traffic to reroute to a different route. Obviously, this alternate route required us to go a much further distance than the original route. Hence, we see latency increases, packet loss increases. So as you can see, if we look back at the first three things that we've talked about, latency, packet loss, and jitter, they highly affect network traffic, and they can be very sensitive. Next, we'd like to talk about bandwidth. And I'd like to clarify a few things right now. Bandwidth indeed does equal network capacity. I'm just going to go to the board for a second here. I always like to use plumbing terms for my analogy. Sorry for the folks on the metric system. I'm here in the US and we're still not on the metric system. But if we have a half-inch pipe, only 1/2 inch worth of water, volume of water, can flow through that half-inch pipe. If we try and put 5/8 inches worth of volume through that pipe, it's not going to fit. What's going to happen? It's going to queue up, right? Again, causing some sort of queuing delay. But the point is that we cannot put 5/8 inches worth of water through a 1/2 inch pipe. So that is a great way to describe network capacity. Now, for all you network managers out there, I have a question for you. When there's some sort of application failure on your network, what's the first thing that gets blamed? Naturally, our network gets blamed because it's never the application's problem. It's always our network that's the problem. And of that problem, what does our novice network engineer tell us, the network manager, to do to fix the problem? Absolutely. Add more bandwidth, because more bandwidth is the silver bullet to fix everything, right? Well, I'd like to disprove that for you right now. And I'm going to go back to the board. So let's imagine this. We're on a single lane highway. We're in a car. We're traveling from point A to point B. Point A to point B are 60 miles, and our car's traveling at 60 miles per hour. How long will it take from that car to get from point A to point B? 60 minutes, right? Let's do this. Let's make it a 2-lane highway. We still have our car. We're still traveling between point A and point B. We're still going 60 miles, and we're still going at 60 miles per hour. How long is it going to take from our car to get from point A to point B? An hour. Did adding 1 lane make a difference to that? No, it didn't. Why? Because whatever our latency value between point A and point B, the laws of physics tell me that at 60 miles per hour, going 60 miles, it's going to take me an hour. I could add 50 lanes or 50 times the bandwidth capacity. It's still not going to make a difference. Where will it make a difference? What if we have a lot of traffic on the road? Let's say we have somebody driving a lot slower than 60 miles an hour. If we were on a 1-lane highway with limited capacity, that would back traffic up and not allow us to go 60 miles in an hour. Now, by increasing our bandwidth, we can actually pass the slow driver, and with more bandwidth capacity, we will be able to go from point A to point B at 60 miles an hour. Hopefully you can see from this illustration that more bandwidth capacity does not necessarily mean better speed. Let's talk about traffic being delivered over a local area network versus a wide area network. What we're dealing with is 1 millisecond going from point A to point B on a 1.5 meg link, or a T1. Now you'll notice, again, using TCP, we know that the importance of TCP is acknowledgement via the 3-way handshake to make sure that our transmission is going from point A to point B. Going over the point of 1 millisecond, obviously those acknowledgements are going to happen a lot faster than they would over a longer distance, because obviously the packets can travel pretty quickly back and forth on 1 millisecond. So in a local area network, which is basically 1 millisecond, we can actually take advantage of that whole 1.5 meg pipe, as you see in the example here. Now let's go look at that same traffic on that same 1.5 meg pipe, but with a little latency added to it. So now again, we have our T1 or 1.5 meg pipe, but we're going over a distance of 200 milliseconds. Notice that we cannot take full advantage of that 1.5 meg pipe size. Why? Because again, with TCP, we have to wait for that acknowledgement to come from our destination before we'll send the next series of packets, thus not allowing us to take full advantage of that pipe size or our bandwidth. So again, this disproves that more bandwidth is going to increase speed, especially in this situation. Now, here's another interesting example. This example is actually bandwidth being saturated over a longer distance. This example was a true example. It happened with one of our clients at Shunra. And what had happened was that there was a client, they had a local office located in Oregon, and their central data center was located in Ohio. The local office was doing all their authentication, file and print, in a server located in their office. The management team decided that they wanted to centralize all their authentication. So what they decided to do was move those authentication servers out of the local offices, in this case Portland, Oregon, and then move them to their central data center in Columbus, Ohio. Unfortunately, this company decided they weren't going to test the results because it's only authentication. How bad could that be? So the users went home over the weekend. On Monday morning, all our users came into their office around 8:30 and all basically logged in around the same time. Lo and behold, after 25 minutes, the fourth user out of 20 finally authenticated. Now, heck, this is only authentication. Why could this be? Nobody expected this, but again, nobody tested it either. So basically, what happened was this company called us in, us being Shunra. We went on site, did some analysis for them, and found out that they were downloading their profiles. A very reasonable security procedure done with many companies, where you're not going to store your profile locally, and when you log in, you're going to download that information. The only problem was each user used almost 1.5 meg to do that profile download. Therefore, when that first user came in, they basically started to saturate the network, and that second user had no bandwidth left to use. When they were locally, they were probably working on a 100 meg pipe, so basically 20 users using 1.5 meg of the pipe locally, where everything was happening over a second or less than a second, there were no issues. But now that you only had a 1.5 meg pipe to go and you had all these users logging in simultaneously, you've used up your pipe, and latency was a factor too because you're going over that distance, but we had multiple users at 1.5, therefore that pipe did not stand a chance. At the end of the day, what this customer decided to do was to authenticate locally. But this is a great example of how all these things working together can produce very bad results over a network. Let's summarize what we've talked about today. We've talked about network delay or latency. We've talked about jitter and how packets can come in out of order because of activity on the line, anomalies on the line. We've talked about packet loss and 5 major factors that contribute to packet loss. We've talked about bandwidth constraints, meaning that half-inch of pipe that we have to use. And we've talked about utilization. If we've used all that half-inch of pipe during a data transmission, there's going to be things backing up if we have 5/8 volume worth of water or data to throw through that pipe.